So before they start that, uh, hope you remember this SN curve now. It's very familiar with you now. So this condition is for the ideal specimen without stress tracer, and this is a non-ideal specimen without stress tracer. So this one is for the non-ideal situation specimen with the stress tracer. So with this stress tracer, you can see the Kf and Kf prime introduced into the equation. So hope you know now. I don't want to explain furthermore this diagram now. And last week we discussed the minor rule, So hope you understand about that. So if we apply the different type of magnitude with the stress cycle, so we need to consider the this kind of statical data. Means then you need to calculate the damage of the damage to the specimen with that stress cycle, particular stress cycle. But keep it in mind. So if the stress cycle is that magnitude, if it is less than endurance limit, you don't want to consider about that stress. So it will not affect to the lifetime of the specimen. So we discuss about this particular example, and the damage around 20% within the 1 hour. So we already calculate the how many hours we can apply this kind of stress cycle. So with that example, we explain the minor rule as well. And then if we have the mean stress and alternative stress together, so we already discussed how we can predict the lifetime. Is it infinite or if it is finite? So we can predict using this this uh, particular line. So those persons are explain the different kind of approaches, but Goodman line is a better one, I told you. So you can x-axis is the mean static. So if alternative stress will be 0, this is kind of tensile test, and this is a fully reverse technique. So there is only alternative stress only applying here. So if both together, you need to consider the Goodman line. So if you want to find out the coordinate with the sigma m and sigma a inside this triangle, I told you it's infinite static lifetime. If it is outside, it is finite. So it has a lifetime. It will break easily with the number there is a value for the number of cycle it can be 7. So we already discussed these things. And when we introduce the stress consideration factor, fatigue stress consideration factor, for the strength, if you introduce, it should be divide. The endurance limit should be divided by Kf. If it is a 10 to the power 3 cycle, it also should be divided by Kf prime. But when you are introducing the fatigue stress consideration factor into the stress, you need to multiply. So according to the question, you need to select which one you are going to use, but don't use both together. I told you during the tutorial also, I already explained. So don't use at those 2 points. If you use for the stress, the stress intensity factor, fatigue stress consideration factor, you don't use again for the strength. So if you use again into this strength, so that Kf will be cut off. So no point introducing the Kf in here as well. So if you introduce in this strength, so you don't use into the stress. So keep it in mind that. And we discuss about this paragraph as well. So if you find out if you have alternative and mean stress together, so you need to find out the maximum stress and minimum stress, and according to that you can find out the coordinate in this graph, on this graph, and the line through that point you can calculate the fatigue lifetime. So you can see. So we already discussed this kind of diagram as well. So I won't ask these questions. Can you answer for this question? What is the main difference between how we can use these figures? So anyone? What is the main difference between So those two diagrams we can use to fatigue lifetime anyway. So what is the main difference between these two graphs? Anyone?
That the graph on the right, you can measure the lifetime for alternating stresses.
Okay. Alternating stress only.
Well, not only alternating stress, but on the left you can't measure for alternating stress.
It's not. It is not the answer. So any others? What is the main difference between these two figures?
So for the one on the left,
Yeah.
it doesn't tell you how many cycles it lasts for, but it does tell you the lifetime, whether the lifetime is infinite or not.
Yes. Then
But
right side one.
the one on the right,
Right side one.
I'm not sure. So I'm looking at.
Right side one. Yeah. The left side one is you can just estimate that uh, now that lifetime of the particular element, is it finite or infinite only. So if it is inside, you can't say what you can say infinite, but if it is outside, you can't say how many number of cycle you can apply to the breaking. So just only you can say it is finite number. It can break something like that. So if it is above the good band line, but the Tihan, as you just show here, alternative and mean stresses. That's why you thought there is a two stresses available, mean stress and alternative stress. But in here also both available. The maximum stress come up with the mean stress plus alternative stress. Okay, minimum stress will come up with sigma m minus sigma a. Are we clear, Tihan? So you can calculate the number of cycle. I mean, you can read the number of cycle if you know the. Last time we discussed the with the theory, we did some example. So if you remember, so we find out the maximum stress and minimum stress around the stress trace area. So then you can find out the coordinate. If that coordinate, so if it is 70 and 20, because somewhere here. So you know it is so in here 10 to the power 7 cycle. So if it is going through this line, that point on this line, you can say the number of cycle to break it 10 to the power 7, something like that. So you can predict the number of cycle as well. Okay, that is the main difference. Are we clear?
Excuse me, sir.
Yeah.
So the main difference is that in the left-hand side one, we can't find the number of cycles.
Yes.
But if it's inside the triangle, we know that it's infinite fatigue life. And in the right-hand side, we can estimate the fatigue lifetime with the number of cycles. Is that it?
Yes,
difference?
that's the thing.
Yeah.
So in here you don't have a number, numerical value, but in here you can find out the answer with the numerical value. I hope you clear about that. Okay, so you can use both diagram for same purpose, but the results will be too different. Okay, are we clear?
Yes, sir.
Okay, Tihana, are you clear about that? Because you gave wrong answer. That's why.
Yes, sir.
Okay. Then so hope you remember this question. We discussed the mean stress and alternative stress together when we apply. So what is the stress variation and the local area stress variation and stress rise area stress variation, and we calculate those values. So we calculate those values to this kind of plate, okay, with the hole. So you can see. So this is the first example, the part A, then part B, part C, part D, and number of cycle to break it. So you can see we calculate those values. Okay, don't refer too much. Then you can see with this kind of stress. So if you remember part B, we apply the free load. If you remember, so I told you if you apply the free load with one cycle, that particular material will be more strength. So you can see, even though the same stress values from since second cycle, there is a locally damage, local deformations are there, but number of cycle to fail, it will be higher. In here, no plastic deformation, because all the around the low stress trace area also stress not reached to the yield strength. That's why no plastic deformation. But with the first number of cycle, so there is a local deformation. Then it will be strength, more strength, and number of cycle will enhance. And the second one, mean stress and amplitude of the alternative stress will be higher. So there is also local deformation, but it is also lower than the yield strength around the stress trace area. So it is lower than this number of cycle, but some significant amount. But if you apply higher mean load and higher alternative load, so the stress trace area will be very high stress. It is beyond the yield strength as well. So ultimate strength or yield strength, so then there is a severe damage. So you can see number of cycle, it is very less. So it is 900 something or 800. It is below 1000. So this is the summary of the example what we discussed last time, the last example, I think. And today we are going to discuss the factor of safety in fatigue. So we already discussed factor of safety, if you remember, in the second lecture, first lecture, I think second lecture, we discussed the factor of safety, and we discussed the 5 methods to calculate the factor of safety, if you remember. Okay, failure mechanism, five failure mechanism predictions we already discussed. So we use some of the technique in here as well, but at that time we discussed only for the alternative stress, if you remember. There is no mean stress. Okay. So when we design something, so there should be some safety factor. Safety factor means the maximum stress you are going to apply should be divided by, so you are going maximum stress you can apply on that specific element should be divided by, so applied stress. So that is a factor of safety. So if it is equal to, like in here, that means maximum stress you can apply on that particular element, it is 2 times which you are going to apply on the specimen. So that is a factor of safety. So you can design according to that if it is 2. Okay, but in here, so if you remember last time in the previous lecture, when I explained the plot the FN curve and SN curve, so I told you better you should select if you select the FN curve instead SN curve, if you remember. So hope you remember that. So I told you there is a reason for that. Rather than comparing SN curve, FN curve is better. So I told you at that time, I will explain later what is the reason for that as well. So now I am going to explain that one. So the loading, when we consider the load and stress, so it can be linear relationship. There can be a linear relationship. Sometimes it is non-linear. If it is non-linear, you can't use stress instead load. So you should use the load values to compare something. Okay, so if you find out the different load value in different areas or different stress trace areas, you need to get the load value instead the stresses, because stresses is not represent the actual picture on that particular element. So you need to consider the load value, force value, because the stress force relationship, it is non-linear. So it can be linear or non-linear. If it is linear only, you can use stress and load both. If you use load FN curve, then if you use SN curve, doesn't matter. But if it is non-linear, you are in trouble. Okay, so that non-linearity between the load value and stress value will be happen because of the element stability. So stability means this: if we apply the particular axial load, the axial as a center axial, so you can see in this element, this is the axial. Okay, so if you apply around this axis that particular P load, this is concentric. Okay, but if you apply that load value somewhere here, so this is we call eccentric load. Okay, because of this load around this axis, there is a bending moment. Okay, so then later on we will discuss about this one as a buckling. Okay, so that particular element will be buckled, and the maximum stress around this point we can calculate using this equation, secant form. We call this is secant formula. So I think lecture 9 is a buckling. So we will discuss about this equation furthermore. Okay, don't worry, that just believe me, this equation, there is an equation like this. So this is in here some of the symbols I will introduce, but I'm not going to prove now this equation, but later on we will discuss about this equation in the buckling session. Okay, so you can see there is a eccentric load. Due to that that particular element, stability will lose. You can see it will buckle like this. Okay, so then the stress and load, even though the when you apply the P load, stress around somewhere here, it is not the linear, it will be non-linear. So you should know that that particular load you are going to apply in axially. Otherwise, if it is eccentric load, so it will not linear, it can be non-linear. So we don't know actually loading is linear or non-linear. So better if you use FN curve. That's why I told you, better if you use FN curve. Are we clear? So in the secant formula, you can see the P upon A, the 2 point in here and here. So I will explain why, what is the reason and other things later in the buckling session. But if that P load applying around this axial axis, around this axis, so you will get the stress P upon A. So you can see that term in here. Due to this eccentric, this distance, this part will introduce. So P upon A times EC divided R squared sec this part. Okay. So in here, E means eccentric, this distance. Okay. And A means cross-sectional area. C means the half of the width of the beam. Okay. So I just explained the equation. I will tell you. So I will prove this equation at the buckling session. And E means same meaning, elastic modulus, and P load. R in here, it is the radius of gyration. In the buckling session, we will discuss about if you have, there can be a different kind of cross-sectional area. So it can be complex. Sometimes it can be the square shape or rectangular shape, very complex shape. So it can be different cross-sectional shape. But you can calculate the equivalent cross-sectional area for that particular complex cross-sections with the circle. Okay. So if you introduce the equivalent cross-sectional area with the circle, that radius called the minimum principal radius of the gyration. Okay. Same cross-sectional area. If you get like this, I will draw here. So if you have this kind of cross-section, so you can't calculate the area and you can't get any dimensions. But if you introduce the circle, assume this is circle. So this cross-sectional area, this cross-section area is, if it is equal, so that radius called the radius of gyrations. So, okay. these two areas should be equal. Then if you got the circle radius, it is called principal radius of gyration. So we will discuss about later. So hope to remember this equation now. I mean, get rough idea about this equation. This is when you apply this P upon A, when you apply the along this axis. But if you apply the as eccentric load, this plus part will be introduced. So you can see the equation now. So yeah, in here you can see in this equation EC divided by R is squared. That part we call in the different name like slenderness ratio. This is called slenderness ratio. This is called eccentricness ratio. Okay, so the buckling I will explain. This we will normally calculate this ratio and substitute in here. Okay. You can see L upon R and EC upon R square. So we can substitute. So they provide in here that part, and elastic modulus provide. And the following figure illustrates maximum stress within the column. So you can see the load versus stress relationship. So it is non-linear. If it is linear, it should be like this. Should be like this. But it is non-linear. You can see. So even though the load, if it is 50 Newton, so you can get the stress with this curve, and if it is 100, you can get until somewhere here it's a little bit linear, but you can see this is the failure load. Okay, sigma maximum is the failure, so 100% failure. So you can see in here, assume this is 165, so it is around 650, something like that, assume. And then when you reduce until 150, 165, if you reduce 150, you can see the stress variation. It is around larger drop in here. You can see, even though it is a small reduction, this is a large reduction. Okay. So you can see there is a severe change, even though load magnitude, if it is changed a little bit, stress variation is very high. You can see if it is 152, it's a large variation in here. So this is non-linear. That's why we can't use stress. When you do some calculation, you need to find out the load value at that point. So are we clear about that? Tihan? Tihan, know someone? Any questions?
Yeah, okay.
And there is some numbers you can deal with that one also. There is a 89 failure load, you can see, and at that time the load reduction around 1.5. Okay, so sorry, stress reduction. But if you reduce load reduce, if it is 1.5, the stress will be much higher. You can see. So you can deal with that, and you can see the main difference in here. Yeah, so I already explained that one. Yeah, as I told you, this is 650, and you can see a factor of safety for an example 1.5 applied to a sigma maximum. Okay, the value of 650 megapascal would correspond to 89% of the failure load. That load safety factor of only 1.12. So in here, if you calculate the factor of safety using stress values, so this is the maximum value. If you are going to apply this value, so you will normally get this value divided by this value, isn't it? It will for assume it is 450. So if it is 650, so 650 divided by 450. So you will get this is the factor of safety actually. So if you divide the maximum sigma maximum by factor of safety, you will get the stress. Okay. So in here you can see in here factor of safety 1.5, but in here that drop explained 1.512. So even though the same stress be relevant to that stress, if you get the load value, it is 1.12. The factor of safety is very less here rather than here. Okay, so it is obvious in this case that the factor of safety should be applied to the load. Okay, are we clear about it?
Yes, sir.
Okay, so as I told you, now we are going to use that particular theory in the alternative mean plus alternative stresses. Okay, so you can see this is the Goodman line. So that's why in here here is ultimate tensile strength. Sorry, endurance limit, and in here ultimate tensile strength. And if you have some coordinate somewhere here, okay, assume this is the coordinate, you are going to apply the sigma m belong to this reading and sigma a belongs to this reading. So this is the coordinate. So if you want to find the factor of safety, what you need to do, this is the maximum load you can apply, maximum stress you can apply. So then what you need to do, you need to find out the this stress divided by this stress. So you can get the factor of safety. Are we clear? Hello.
Yes, sir.
Okay.
Okay.
So this is the as I told you, you need to keep it in mind in here. Even though this this particular graph belong to stresses, we need to consider the load value around here. Okay, the maximum stress load value. Okay, don't use stress value. So load value in here and load value in here. So you need to get the ratio between these two. It is a factor of safety, but you don't want to find out those coordinate. If you have this x-axis coordinate, that is enough. This is the projection of this curve, this length, isn't it? This is the projection of this length. This is the projection of this length, and then you can find out the OB divided by OA give the same ratio. OP divided by ON and OB divided by OA or OE divided by OD is given the same ratio. Okay, that is a factor of safety. Are we clear?
Yes, sir.
Okay, so if you apply the, but in here the you can see sigma mean stress, that means a mean stress and alternative stress will be increased the same amount. Okay, same portion. If you increase the 10 megapascal in alternate main stress, you need to increase the same amount of alternative stress. Then only you can use this technique. So if you use this way, if you not increase the sigma m, only if you increase the sigma a, so you need to get the ratio like that, like this way. Okay, factor of safety you need to get like this one, because you are not going to increase the sigma m. It is constant. Are we clear? So you need to get the OQ divided by, QA divided by NA or F divided by OD. Okay. Then in here alternative stress not change, but only mean stress will be changed. Then you need to consider this this line. So OC divided by OA or DR divided by DA, doesn't matter. But assume somewhere here, if you are in somewhere here, so then the increment will be changed. You can see the mean stress will be highly increased, but alternative stress not highly increased. Then you need to use this line. Okay, there is only 3 cases explained, but if you increase alternative stress very highly, I mean increment is very high rather than sigma m, then that line will be somewhere here. Okay, so you need to calculate the according to that. So this is general 3 case. Yeah. Yes. To this point, we have considered only simple loading, axial and bending and torsion. So if we have combined these three loading, what happened? So if normally you calculate, if you remember, only for bending, okay. Sometimes you deal with the axial load only or torsion. So we didn't discuss if the load those type of load applied together on the element, what happened or something like that. So combination of loading we will discuss since now. Okay. Then we will calculate the factor of safety as well. So we already discussed the factor of safety, how we can calculate another thing. So according to that, if you can apply the combination of load on the element, and we can calculate the factor of safety as well. Okay. Are we clear about that? So hope you remember we discussed until today we discussed only one simple loading method. If it is bending only. If it is torsion, in that question only torsion or axial only. Okay. There is another assumption. So many assumptions are there. Okay, so in here there is assumption. What is the assumption in here? In here, if you are going to apply the stress to find out the factor of safety, that particular loading condition should be linear with the stress. So it should be linear. Loading and function of loading and stress function should be linear. But if it is non-linear, you can't use stress. You need to use load value instead of the stress. So normally if you use stress, you will assume it is linear. So you need to mention it. And there is another assumption. This assumption you need to keep in mind. So if there is alternative stresses, those stresses are simultaneously reach to the maximum value. That's mean I will draw here. So if we have, I'm sorry, if we have, okay, this is one alternative stress. So there is another alternative stress on the same element. So with the different magnitude, you can see, assume this is passed through this point and this is passed through this point. You can see those two alternative stresses will reach maximum simultaneously. So same phase. If it is different phase like this, okay, if you apply the stress like this and another stress, if it is different frequency actually. So this is not the same phase. Those are different phase. Okay. So we will assume that alternative loads are in phase. Are we clear about that? So there is another assumption. Otherwise, if it is changed like this, so calculation will be different. That's why. So are we clear about in phase and out phase? Yeah. Can you hear me? This connection is. Hello.
Yeah, we can hear you.
Okay. So is it clear? Is it clear about?
Yeah.
Okay.
So, sir, both like the peaks, like they have to be in phase, right? For this
In phase.
assumption.
Yeah, assumption.
If they're out of phase, they can't.
That I couldn't hear
That
properly.
cannot be used. And then the other assumption
Premi,
is
I can't.
like the other.
Can you repeat it again?
Hello.
Yeah. Can you repeat?
And the other, now there are two assumptions up to now, right?
Yeah.
So the first assumption is that the stress should be stress and the load. Stress should be a function of the load, and that should be linear if you are using the stress, right?
If it is non-linear, you need to use load value. So at
Yeah.
the very beginning, you need to decide is it non-linear or linear.
Okay.
Second
And
one,
the other one is the alternative loads should be in phase.
yeah, should be in phase. If it is not in phase, the calculation will be different. That's why.
Okay.
Okay. So in this module, you don't have that out of phase alternative loads. Okay, just only in phase. But assume if they ask the questions at the exam, what are the assumptions you will make, you need to note down these things. That's why I'm highlighting these things. Okay. So normally you will note down some general thing, but you will get the marks for these things. Okay. Then yeah, zero mean load. Zero mean load means there is no mean load, only alternative load. Okay, don't worry about that too much. So we will discuss for this thing for the ductile material, so not for the brittle material. So brittle material, we are not going to use so many loading combination of load. So normally it will use for the compression load only. So we are not going to bend glass material. You are not going to bend glass material. You are not going to apply the tensile load. You normally will apply the compression only. Okay, so this particular theory belongs to ductile material. Okay, that's why in here zero mean load ductile material. I think you remember this one as well. So we already calculate this one, and in the maximum distortion energy theory, the load factor for the CL is 0.58. If you remember, for the torsional loading, we discussed this one lecture number 3 or 4, I think. Okay, so just refer that one. So we already discussed for the torsional load CL value. If you select check the table also when you do the sum calculation, if you're going to find out the load factor, the torsional load CL value will be 0.58. But we proved that earlier. Okay. Since the maximum distortion energy theory predict this for static biaxial load, torsion and experimental data confirm the choice. Yes, we already discussed this one because we need this one. That's why I explain here. Tests have been conducted for various combination of bending and torsion load, and it is found that the maximum distortion energy theory predict the fatigue failure of these quite well. We already know that. So normally the failure mechanism we can predict for the ductile material using von Mises theory. That means the maximum distortion energy theory. So hope you remember what is the maximum distortion energy. Okay. So there is no, without destroy the shape of the animal, how you can apply how much you can apply the energy on that. So that is the strain energy you can apply until change of the specimen shape. So if it is shape change, the maximum distortion energy you can't apply. So at that time, shear stress should be equal 0. So you can apply only the maximum distortion energy for the principal stresses plane, if you remember. So you need to find out the principal stresses at that point in the Mohs circle. Also you can see the shear stress will be 0. So this is the previous lectures. Okay, so remember. Okay, so in here the first quadrant of the you can see first quadrant of the maximum distortion energy theory, that is a DE. Okay, distortion energy theory. And shear stress theory, Tresca theory, if you remember, Tresca theory, third method we discussed. the lecture number 2. So shear stress theory, that means Tresca theory. From the Tresca theory, you draw the boundary line for the failure mechanism. If you remember, there is a maximum principal stress theory like this, and then then strain energy theory, and then there is like this strain theory, maximum strain energy theory, and maximum distortion energy theory, maximum principal strain energy theory, and maximum shear stress theory, like that. So this is the first quadrant. Okay, in here you can see, and this is divided by this x-axis is alternating bending stress, divide by bending fatigue limit. So don't worry about this. Is kind of we call this is generalize the equations, I mean curves, because if we divide from that particular parameter by constant value, you can see this one and this one is same thing. So if you divide, this is constant value for the material, so if you divide the parameter value from the constant value, so this will be linearized actually. So generalizing means that, so you can, so you will get the, so if assume this value is 1000, so you need to get the actually alternative torsional shear stress by multiplying 1000, so it will be 800. So this axis and this axis is very lengthy, so if you can compress this curve using the some constant value and divide that particular the value by that constant value, so that x-axis and y-axis will be compressed and you can clearly predict. So that's the reason for the generalization. So don't worry about the dividing part. So you can see more than shear stress theory. So you can see DE theory is valid for the, that means distortion energy, maximum distortion energy theory is valid for the practical things. Are we clear? So these are the practical data points. So they didn't check for the all the alternating bending stresses, but bending stresses and shear stresses, we just check it for the some specific values, and that actual data around this DE theory you can see. So it is more suitable for the predict the fatigue lifetime for the ductile material. So this graph explains that.
Excuse me, sir.
Yes.
Why do we call that the zero mean load? Like, what is
Zero mean load,
like-
there is no any mean load. Constant load we are not going to apply, only alternative load.
okay?
That means sigma m equals 0 in here. Okay.
Oh, sir.
Only alternative load.
Okay, sir.
Okay. So this is you can see. So as I told you, you can't apply the DE theory. That means maximum distortion energy theory with the shear stress. That means shear stress should be equal 0. It should be absent. So then you need to consider the sigma 1 and sigma 2 principal stresses. If it is only if it is zero main load, there is no any main load, only sigma A, alternative load only. So you need to find out the sigma 1 and sigma 2, maximum and minimum principal stresses. So this is the curve for the DE, you can see. So we already know this is the curve. And
So these von Mises, right?
yeah, von Mises, yes. Von Mises theory, last theory, fifth one. So in here the compression, this is tension, this is tension, this is compression, this side. So you can see you can draw the line in here. This is assume this is 45 degree. So you can see the mirror image of around this axis. Okay. So in here torsion will be applied. Okay. So reverse torsion. Okay, because in here you can see these two. This is like a circle squeezed to the these two directions. Then that circle will be elongated to this axis, and it will be compressed to this axis. So this is torsional. Okay. So don't worry about this one too much. Just for example, explain the DE theory and DE theory. That means the von Mises theory is more suitable for the calculation. That's why. Okay. So this is the fully reverse bending technique. Okay, this is also fully reverse bending, but it is a compression size. This is tension side. Okay. I hope it's clear. Yeah, the same thing. So with this example, you will easily understand what I am explaining. Okay, so I will read the questions, and so this kind of questions you don't have too much data, so you need to identify the things in here. Okay, so you can see they ask estimate the alternative force F. That means this value. This is alternative force. You can see it will be go downward and come upward. So force F, which would be just sufficient to cause eventual fatigue failure of the bar shown in SU. It is equal 621 megapascal, and that's why that means yield strength is 379 megapascal. You can see there is a key base. Okay. So these are the weaker point. So in this shaft there is no any other weaker point. Okay, this is loading point. This is the weaker point. And if you apply load like this, it is in y-axis actually. So if you apply the load in y-axis, so A and B, that 2 points are, if it is going to downward, A will be under tension. Okay, tension means it will be the highly stress, and this will be highly compressed. And if it is come upward, so then the B will be high tension. This will be compression, and C and D also in the tension and compression. But when you consider A and B, C and D is not significant, isn't it? So you need to consider the A and B stress variations. Okay, so these are the stress raises areas. So A, B, C, D. So you need to consider A and B. That's how we can select, because this is a, if you apply this kind of so in here, if you apply the x-axis around x-axis load value, then C and D under tension and compression. So you don't want to consider A and B. So in here it is around y-axis. Okay, towards the y-axis. So you just use to A and B. Yeah, the critical location will be at A and B. Bending stress and maximum and torsional stress exist. There is this is also the location of stress raiser, as I told you. Okay, so that doesn't mean C and D is not weaker, but when we compare those 4 points, A and B is a critical point. A and B is reached to maximum stresses. That's why. So we don't want to calculate C and D then. Okay. So since the different loading will be will give different value of K F, if it is based of K as a stress concentrated factor applied to each load rather than strength reduction factor. I told you. So in here, you need to decide you are going to apply the fatigue stress concentration factor into the strength or stress. If you apply into the stress, it is better rather than strength. Okay, so don't use in the strength equation K divide by Kf. So you need to multiply stress by Kf. Okay. So there is a, okay, before I start the question, I need to explain the loading pattern. So this is due to this F load, this shaft will be bent, isn't it? It will bend downward, and if it is upward, it will bend upward. And same time, due to this distance, you can see, so even though this F load apply in here, the bending is same. Okay, the bending of this shaft will be same. But thing is, due to this distance, there is a this cross section. I will draw here. Okay, this is the cross section here. Okay, this cross section try to rotate due to this load, because this is eccentric load, so kind of eccentric load. If we apply this F load somewhere here, it will not going to act as a torsional load, but only bending load. But if you shift this F load to this distance, or if you apply in here, it is also applied as a torsion load. Okay, so it will try to rotate. So this is shearing. Okay, it acts as a shear load. Are we clear about it? So there is a two type of loading, combination of two types of loading: shearing and bending. No axial load, shearing and bending. Okay, so that's why in here, when they calculation, they are use the due to bending. So normally we are not going to apply the theory. So bending and torsion and axial, three type of loading three loading type, we assume there is another assumption. We assume they are act as independently. So we can use superposition theory. Okay, that means we can calculate each and everything separately and combine later. Okay, so due to bending part you can do that. Then due to torsional part, if there is axial part, due to axial part you can calculate separately, and later on you can combine. Okay, so due to the bending, so you can see this is the shaft, this is the load. So you can calculate the first KT. So you can see here KTB, that is meaning of due to bending. Okay, KT value due to bending, because KT will vary with the type of loading. If you remember, so if we apply axial load, KT graph will be changed. Okay, so this is if it is bending. So when you calculate the KT value due to bending, it is different. Same shaft, same load, but even though same load, the KT value will be changed according to shear and torsion and the bending. So due to bending, KT value, when you're going to find out, you need to select the proper graph. This is the shaft. Okay, so you need to select the ratio. I mean, find out the ratios, RD and capital D divided by simple D ratio on the shaft. In here we are consider this region. Okay, even though you can see the shaft this much of length shaft, you will consider somewhere here. Okay, so you can see here diameter of this large part and smaller part, diameter 12.7 millimeter. Okay, so that's why this is ratio. So you can calculate KT. I'm not going to explain that one. So I just want to focus in here. You need to find out the KT value for bending. So in here B means the due to bending KT value, and you can find out the notch sensitivity. So it is also changed according to loading type. So if it is a bending and axial, you need to consider these. You know ultimate tensile strength. You know notch radius is 2.54. So you can find out the Q, notch sensitivity factor, get the reasonable value. Then you can find out the KF. CS also you need to find out. So CS not going to change even though it's a torsional or bending, doesn't matter. So you can calculate the is machine sample, you can find out CS and then find out the KF, but due to bending. Okay. So due to bending, KF value you can find out using this equation. I hope you remember this equation. So then you have KF value for bending. Then torsion. Due to torsion, you need to find in here KT within bracket there's another T. It is denote the torsion. Okay. Due to torsion, KT value. So you need to find out the ratios. In here, the ratios will not change, but only change in the graph. So this is the graph you can see. So then you can find out the KT value due to torsion. Then this is the KT value, approximate value. And the Q value, you need to again find out, because due to torsion, you can see this is the relevant value for that. This torsion, if you want to find the torsion, for the torsion, if you're going to find the Q value, you need to use these values. So if it is 621, according to that, you need to find out this value when the nut radius not change. So you can find out the Q value. And CS not going to change, same thing. So you can find out the KF, that means fatigue stress concentration factor for the torsion. So you have that now KFB and KFT. So then you need to consider point A and B, that is stress laser areas, it's highly significant two areas. So sigma value. So if you don't remember those equations I told you, you have those equation in here. Okay, don't worry about them in this graph in here. Okay. So this is the equation for the bending. Okay, so you can see here 64. When you cut off by 2, it will be 32. Then this will be d cube. It's the same equation that I show you. So in here, the y means distance from the axis, if you remember. So this is to A, point A, from the center of the cross section. Distance is d upon 2. So for the B also, distance d upon 2. That is the y. So bending moment, we know what is the bending moment. So even though force apply here or here, doesn't matter. This distance govern the bending. So F time this distance, you can see here. It can be plus or minus, because it can be go to upward and downward both. So this distance govern the bending part. This distance govern the torsional part. Okay. So this is the bending load. So bending moment. So you know the d value. Diameter you need to divide by 2. Okay. So that distance, y value. This is the second moment of inertia of the circular cross sections. And you need to multiply here KFB. You can see here, because we are going to calculate the stress due to bending. And I told you, you need to introduce KF, that means stress, fatigue stress consideration factor, into stress. So in here, you need to multiply. So then you need to substitute in here for the bending moment and D values. So F is the unknown thing. We are going to find out the F actually. So F will be remaining here. And you can find out the sigma A, that means alternative stress, point A, due to bending. Okay. Then torsion. So it's torsion equations. So I show you already. This is the equations, and you will find out the A and point B, A or B, the torsional load. Torsional load will be, torque will be like this. Torsion. So this is the load value. So you need to find out the torque by multiplying this distance. It can be plus or minus, because if it is upward, it will try to rotate this direction. So D value you know. So then you can find substitute here and find out that alternative stress due to torsion at point A or point B. So this is the alternative stress due to torsion. This is due to bending. Then what you need to do, this is very basic theory now for you, because we already did some so many example with that one. So you can draw the Morse circle, or if you want to use equation also. Anyhow, you need to find the principal stresses. Okay. Using the maximum distortion energy theory, we wish to determine simple reverse bending load equivalent to the combined effect of the above load, which will cause eventual failure. Okay. So you have, if even though you have too many stresses, you need to calculate the one equivalent stresses, one equivalent stress. Okay. But you can't use shear stresses. You need to eliminate the shear stresses. For that, you need to find out the sigma 1 and sigma 2 minimum and maximum two stresses using Morse circle theory or using equation. So anyway, you already find out the torsion shear stress. This is shear stress. This is bending stress. So this is, you can see, in here you can see this is the this value. Okay, and this is shear stress. Okay. So you can either equation or Morse circle theory you can use, but if you use Morse circle theory, so there is a sigma y equals 0 in here. Okay, so one coordinate on the Morse circle 0 and minus 2.22 times 10 to the power 5 f. This is the one coordinate, and another coordinate, this is x coordinate, this is y coordinate. You can see here, and you can draw the line and you can get the center, then draw the circle, and you can find out these 2 points. And using Pythagoras, you can find out the radius as well in this circle. If you know the radius, you can find out the sigma 1 and sigma 2. Doesn't matter then. Okay, and you need to find out sigma 1 and sigma 2, or you can use this equation. You don't want to use more, if you're not too much familiar with the Morse circle theory, they didn't tell anything to use. So if they mention using Morse circle theory, you need to find out the equivalent stress. Definitely you need to use this technique. They didn't ask, you can use equation as well. So if you remember the equation for the maximum principal stresses, so you can use this equation. We already derived these equations. Then substitute here. After substituting, you can solve the equation. So sigma x equal this value, tau xy equal this value, and sigma y equals 0, as I told you. Then substitute here, you will get the sigma 1 and sigma 2 like this. Okay, so using this Morse circle also, you can find out these values. At that point, shear stress will be 0. Okay, that's why we are going to find out sigma 1 and sigma 2. Then you can substitute in here. Then you need to find out the equivalent stress. So equivalent stress in here. Just substitute sigma 1 and sigma 2. You can see this is the equation. Sigma 1 is squared plus sigma 2 is squared minus sigma 1 times sigma 2. So that is equivalent to squared value of equivalent stress. So then you will get the sigma equivalent like this. Okay. So you have one single stress represent both stresses. Then you already find out the stress now. What you can do, you can find out the strength, but don't introduce Kf in here. I told you. So you can substitute here endurance limit, and CL you can find out from the table, and CD, the dimension factor, is also from the table, and surface factor we already find out. So you can substitute here those value, and you will get the endurance limit, that means infinite fatigue lifetime strength. Okay, so that is strength you have. So this is strength and this stress should be equal. Okay, this one and this one should be equal. So if you introduce kf in here, you are in trouble, okay, because then that kf will be cut off, and you can't apply in kf in here as well. So it is not a one single thing. So we need to find out separate this torsion and bending. So that's why we are going to introduce kf into stress, so that stress value and strength should be equal. Then if it is equal, so you know this is 7.4 times 10 to the power 5 times f. So that pass in here, and if in subject, then you will get the load value. So this is the load value you can apply the maximum load without breaking. So hope you understand that example. If you have any question, you can ask. Are you there?
Yes, sir.
So did you understand everything?
Yes, sir.
Any questions until this point? Because now it will be a little bit complicated. Okay, that's why I'm asking. So if you don't understand, you can ask and to clarify the point. Otherwise, it will not useful in conduct this session. So how many participants are there? Need I mention the name? Pramit? Did you understand? Senal?
Yes, sir. I understand.
Fermi? Akil?
Yes, I understand.
Virant?
Yes, sir.
Virant?
Yes, sir.
Okay.
Yes, sir.
So need I ask?
So I think we just need to do some questions, and then we'll see if we properly understand it, and then we can come and ask you next week if we.
Okay. And in the Zoom session, if you raise, there is a tool to raise your hand, no? But even though you put the raise your hand in, there's a button you can raise your hand, isn't it? I think you
Yes.
know that.
Yes, sir.
So, but I can't see that because I am sharing the slide. Slide no. So better if you have something to ask, you can raise your hand, voice. Okay. I think it's
Sure
clear.
thing, sir.
Okay.
Okay.
Yeah.
So I will continue then. Okay. So until this point, we discussed the zero mean load, how we can deal with the zero mean load. Now we are discussed the mean plus alternative combined stress. Okay. So I mean, until this point, we discussed zero mean load means with the fatigue stress. Okay. If sorry, it's factor of safety. If you are going to find out in this session, we discuss this part for the zero mean load. Previous lecture also we discussed mean load and alternative load together, but do the calculation in here we discuss only alternative load, okay, not the mean load. So now we are dealing with the mean load plus alternative, okay, mean load plus alternative combined stress. So we should know how to use that maximum distribution energy for that, and we can apply that one. The maximum stress, last time we discussed, if we apply the main load plus alternative stress, okay, amplitude of the alternative stress, minimum one is sigma m minus sigma a. We already know that. So, but there is no particular technique to, I mean, find out the I mean mean plus alternative combined stress where we need to use the KF. There is no any significant method, but better if you use for the stress again, okay, stress raiser. So there is a steps when you do this kind of question, okay, you need to keep it in mind. So you need to follow this step if you have mean plus alternative stress, okay. So the mean load means it will be the axial load, okay. You doesn't have axial load in that particular question. There is only torsional and bending load. So alternative stress should be combined to obtain an equal alternative stress in order accordance with the maximum distortion energy theory. As I told you in this first example we discussed now, if we have different type of alternative stresses, that's why in the assumption I told you that alternative stresses should be in phase. If it is not in phase, we can't calculate the equivalent stress for that. Then we need to use another theories, different theories. If it is in phase, we can easily calculate the equivalent stresses using von Mises use the von Mises theory. So if we have different type of alternative stresses in the question, what you need to do, find out the all the alternative stresses with multiplying kf, then get the one single equivalent stress like sigma equivalent earlier what we got. Okay. So you need to get the one single equivalent stress, and then you can apply the maximum distortion energy theory. An equivalent mean bending stress should be used, which is the maximum principal stress which is caused by mean load component acting alone. Following the residual stress method previously derived, mean stresses are also increased by Kf. Yeah, that is obvious. Mean stresses also should be multiplied by Kf. So you have in here same example you can see. Okay, so estimate the alternating force F, which would be just sufficient to cause eventual fatigue failure of the bar shown, which has a static load of 223 Newton. That means in here constant load also applies 223. Okay, so with this F load they will apply 223 constant load as well. All the time there is a constant load applied, so it will be something like this. Earlier it was fully reversed like this, now it is shifted to upward like this. Okay. So this is main load, this value is main load. Okay. Other values are same, dimensions and ultimate tensile strength, yield strength, all the things are similar, but the only difference there is a plus 223 values. So let's see how we can deal with this kind of questions. You can see that if we don't have 2203 constant value, that means mean stress, if you don't have, you can use Goodman line like this way. Okay, you can see here we already find out this is stress strength SN value, if you remember. I will go back, then this value. Okay, this value. So if we don't have mean stress, this is the SN value, and in the Goodman line the other end will be SU. So we already have SU value, so this is the value. So you can draw the line, Goodman line. So here always we assume CL and KF will be equals 1. If in here KF also vary, so you can see the strength will be reduced. If you introduce in here KF, it will be reduced. Okay, so we assume KF equals 1 in here, because we introduced to KF value for the stresses. So we don't want to worry about the calculate the F, then we can easily find out the F. But in here, if we have, we didn't introduce the KF value for the strength, that's why in here KF equals 1. So this is the normal Goodman line. Okay, so you need to find out the required curve for this one. So let's see how we can deal with that one. So mean stress, even though mean stresses also apply, that mean stress also act as a bending and torsion. because the same point, same direction it will apply. Only different, it is constant load. So same equation you can use, and same kf value you can use. So you can see in here the mean, for the mean stresses we are going to find out the shear stress. We already find out the kft in the first example. So kft same value, if you check you can see same value. So torsional load in here, torsional load apply with the, we have the diagram, if we don't have diagram in here you can see same load value, same distance. So this is govern the torsional load, this distance govern the bending. So due to this load, bending and torsion again it happens. So we already calculate the equation for the alternative f value, and now we need to find out the constant value stresses. So you can find out this way. So but at the exam you can't do like this way, okay, because you need to start from the beginning. You need to do the all this step in the example 1, then second, this part is you can do the secondly. So in here we are not going to discuss again that same part. So mean stress you can calculate for the mean stress you can calculate the shear stress and then bending stress sigma then tau xy you can calculate the substituting. This is the torque due to this constant load, and this is the radius distance, and this is the j value. Then you can find out the shear stress due to mean stress, okay, due to mean load. And then sigma bending due to bending moment, you can find out the due to constant load you can find out the bending moment with this distance, calculate it, substitution, and the bending stress. So now we have shear stress and bending stress due to mean stress, mean load value. Due to mean load value we have shear stress and bending stress. So similar to first example, this is due to mean stress. What is the sigma x, and this is tau xy. And then use a maximum principal stress theory. You can use the equation O Morse circle. So you can find out the sigma 1 and sigma 2. Okay. Then what you can do, that particular line you have, that the first case. So what you can do, when this line equation you can find out with the gradient. Okay, what is the gradient of this curve? So if it is tan theta, you can find out, you know this distance, you know this distance. So theta equals tan inverse this is divided by this one. Okay, so this is the gradient of that curve, and this is x sigma m, that is x. This is the intersection, so you can see this is y. So you have that line equation. So if you know alternative stress, you can find out the mean stress without calculation. Okay, because if you know the if you know the equation of this Goodman line, you can easily do that, because we already, you need to find out these value like first example. Then you have this particular line equation, then you can find out the sigma a, sorry, sigma m. If you know sigma m, sigma a you can find out. If you know sigma a, you can find out sigma m. You don't want to do the calculation again. Okay, so we in here we know the sigma m value. In here sigma m value we know, so you can find out sigma, you can substitute here sigma m. Sigma m maximum value, if we know, we can substitute here sigma m maximum. That is the maximum value reached by sigma m. So in here it is 157.5. So this is x coordinate. You can draw the line. So that is the y coordinate one of here. You can easily find out if it is a scale graph. You can easily find out for the coordinate, but if it is not a scale, you can use this equation and find out the sigma A. So this is the alternative. Yes.
I have a question. So, is this always the case that the maximum mean stress is equal to the principal stress? Is that always the case?
I couldn't understand what you asked. Maximum.
You said sigma 1 is equal to sigma m maximum, right?
Sigma maximum. Yeah, because
Hello?
yeah, sigma 1 means the we calculate the sigma 1 for the, can you hear me?
Yeah, I can hear you.
Sigma 1 means due to mean stress, we will apply the constant load as a mean stress. That is 223 Newton. So that is stress. Due to that stress, there is a maximum stress on that element is a sigma 1, isn't it? Using this Morse circle, you can see this is the maximum stress. So using that equation also, sigma 1 means due to that 223 Newton, sigma 1 is the maximum stress apply on that element, isn't it? More than this stress, there is no any stresses beyond this value. You can easily see this Morse circle here. So this is the stress that 223 Newton value reach the maximum as a maximum, isn't it? So we need to find out the maximum values for the calculation. So you can in here you can see sigma 1 equals sigma m. Sigma 1 means the maximum principal stress. So maximum principal stress is equal to the maximum mean stress, isn't it?
Yes, sir.
Are we clear? So
is that always
all,
the case? That's always the case.
All other stresses are below that stress. So if you find out the the answer for the maximum one, you don't worry about the lower one, isn't it? Are we clear?
Yeah, that's okay.
Okay, so this is the maximum one. So then you can find out the sigma A. Then that sigma A should be equal to this value, because we already find out that value. Okay, so F is the variable thing in here. So even though you do the calculation from the beginning, you will end up in here for the sigma A. That means the alternative stress. If you remember, so same calculation you need to do in here, sigma A. So you will get this value. Okay, so in here you will find out the F value for without mean stress. Now we are going to find out the F value with the mean stress. Okay, so maximum alternative stress you can apply on this element with the mean stress. Now we are going to do. So in here you can see this value. Sometimes you will be surprised how we get the directly in here. Same calculation. Okay. So you will get this value. This should be equal to calculation from you got from here. So then you can get the maximum load you can apply in here as an alternative load. It is 214.7. Earlier it was a 270 or 80. I don't know. I didn't remember. So then the maximum load you can apply, you need to get the summation of the mean load and alternative load. That is the maximum load. Okay, so you can find out the stress without any problem. You can substitute into that equation. This equation, if you find out the maximum load, because maximum load means on the element maximum load, the mean load plus alternative load, sigma m plus, sorry, F in here mean load, sigma m. Due to sigma m there is a load, due to sigma there is a load. So you can find out that load value then you can substitute here, then you can find out the stress, equivalent stress. So it is below the yield stress, so there is no any yield, it will not break. That's the meaning of that. Are we clear about that? Sometimes you will confuse, that's why I'm asking. Any questions?
Sir?
Yeah.
Why did we have an assumption as CL equals 1 and KF equals 1 earlier in the slides?
In here, I think you are asking from here. Okay.
This one, yeah.
Okay. Okay, so Sn, we are not going to introduce the stress intensity factor, that means fatigue stress concentration factor into the strength. That's why. So if you are not going to introduce mean Kf always equal to 1, isn't it? If you remember when you do the calculation last time in the tutorial, at the loading point there is no any stress razor. So that means the Kf equal 1. Normally stress razor, if it is introduced, Kf value will be lower than 1. That is a normally, that's a thing normally will happen. Okay, isn't it? If you remember. So normally in this kind of questions we are not going to introduce Kf into the strength. We will introduce the Kf for the stress. So when you draw the Goodman line, we will consider Sn and Su. So Sn will be 215.2 according to this equation. You can see here. In here, you can see here. So if you introduce here Kf, this value will be so F value will not change, but that stress value should be divided by Kf, then this value will be different, because this 7.48 will come due to this Kf as well. So we already introduced here. Okay.
Yeah.
So if you introduce again that Kf in here, you are doing some wrong calculations. So then you can, what you can do, you can calculate the, but you can't find a single Kf value in here. That's why we need to introduce the stresses. So strength we will calculate for the one single component, as a single value. But there is a two type of stresses. So you can't use one Kf value for all the stresses, all the type of stresses. So you can't divide K from the Kf in here because there is a two type of stresses. So normally what we do is we are going to introduce that Kf value, the stresses. So then we can calculate the load. We are not deal with the stresses now. We will get the answers for the load. So don't worry about the stresses then. So we can find out the load value. But in here, you will not introduce Kf. Due to that, the Goodman line Sn value will be this value. So in here, Kf equal 1. Actually, Kf is not equals 1 in here as well. But we can't get the one single equivalent Kf value for the both load type. Did you understand what I'm explaining? There is a torsional load and bending load. We don't have one single Kf value. So what we did normally, we will separately apply to the stress value, that Kf value, relevant Kf value, and calculate the equivalent stress value, and it should be equal to the strength. Are we clear?
Yes, sir.
Okay. So that's the thing. And so in here, the surface nature, the fracture surface nature and observation, you can see, I will explain. So there is so many images you can see. And so can you communicate with me in this when I explain this one? Otherwise, it's like a one-way communication. I will ask the question and give the answers. It's not good. So in here you can see the different type of images. So okay, so I hope you know what is the. I already explained in the lecture number 2 1. So this behavior. So how many, if you remember? So okay, what are the failure type we can occur in here? What are the failure types? I mean, there is a 2 type failures, brittle and ductile. Okay, so in here this one is brittle or ductile.
Brittle. It's brittle.
This one.
That's ductile.
Okay, I think you are saying it's a brittle or ductile. Okay, what is the reason for this is brittle and this is ductile?
Because the brittle material will have a more like sharp cut, and the ductile will have a sort of elongation and then a snap.
Okay. What can I tell you? Okay, in both of them has a ductile and brittle both. Okay. So this is the combination of ductile and brittle failure, both of. But in here, significant failure will happen due to ductile. We can say like that. So you can see there's a shade area. The shade area, it is due to brittle. This you can see this like a there is a kind of line you can see. So this there's a contours you can see. That contours due to ductile. So you can see in here that contour area and the shade area is significantly higher than the contour area. So this is okay, 60%, 65% or 70% due to brittle. So then we can say brittle like that. So there is a combination of failure. We can't account to one type of failure method in here. You can see the brittle and ductile all together will happen. Okay, are we clear?
Yes,
Sir,
sir. But the low nominal ones, like majority of it, mainly ductile, and the left side ones mainly brittle, right?
Yeah, that's what I'm telling. So in here 90% ductile, in here 60 or 70% brittle. So according to that, we can say this is brittle, this is ductile, something like that. Okay.
So sir, the contour lines indicate that it's ductile in failure, when the shaded area means it's brittle.
Yes. As Tihan said, this is kind of flat area. Okay. The shade area. This is happened. Okay. How many crack initiations are there in here and here and here? Okay, here. Okay, let's see. Okay, this figure and this figure. Okay, in here, how many crack initiation? Crack initiations is where? Here, here, here.
So is it one?
One crack initiation. Where is it? In here, or here, here, here. I will go take around this arrow. You can see.
So my guess would be where the ductile and brittle meet, or is it at the top where the circle is?
In here.
I think, yeah.
Yeah, this is the crack initiation point. Okay. So you can see the contour lines. Normally, it is that crack initiation point. It acts as the center point of the contour. You can see. So you can see here, this is crack initiation. In here, crack initiation. There's another one. There's a 2 crack initiation. There's a 2. So that's how you can identify. So this is very important. You should have idea. So even though if you are going to industry or the manufacturing productions company, so you should, if as a mechanical engineer or material engineer, as an engineer, so you should have idea. So the component, if it is fail, some particular component, if it is fail, so you should just watch it and observe the features, and you should tell, okay, this is due to sometime overloading. This is sometime due to high frequency of load apply, something like that. You should have ability to tell with the observation. So with this cross-sectional observation, you can say that. Okay, that is a very important thing, and then you can do the testing on it and you can check it later. But you can predict very early. So this is the reason, and you can check with that. Your okay, you have some hypothesis. So you think, okay, this there is a over stressing. Due to that, you can do some experiment on it, and you can give the solution for the company, something like that. So that is the importance of the cross-sectional identification. So you have idea of the characterization of cross sections. So there is so many.
So is there no crack?
Yeah. Why I didn't.
Sorry, quick question, sir. So is there no crack propagation due to brittle circle? Is that's where the ductile, the circle is where the ductile crack happens at the top of the.
In here.
This
in here.
Yeah. And the circle is what indicates the crack propagation.
Yeah.
But for any of these diagrams, is there no crack propagation due to brittle?
Crack propagations never happen due to brittle, because if you remember this diagram, I will draw in here. So brittle material doesn't have plastic deformation, if you remember. That's why you can't see any line of that.
Okay, yeah.
So these lines indicate the plastic deformation. Okay, we call it slipping. So normally brittle material doesn't have slipping. Okay, it will suddenly break. You can see. Okay, I will explain furthermore in here with that question. So you can see here these cross sections. So at the very beginning, whole cross sections govern the stress. Okay, so assume that cross section will be like this. Okay, this is the side view. Okay, this is the cross section. So you will apply the okay, bending load. Okay, this is the cantilever beam. You will apply the load, something like that. Okay, the whole cross sections govern the, I mean, it will maintain this stress. But if there is single crack, what happens? This is the effective cross-sectional area, this area, isn't it? So when crack propagate, what happens? Effective cross-sectional area will be reduced. Okay, at one single time. So somewhere here, so this will be the effective cross-sectional area due to this crack propagation. So you can see here. So due to that this effective cross-sectional area is reduction, this load we cannot withstand with cross section. It will suddenly fail as a brittle material. Okay. So until this point, it acts as a ductile material, but with the effective cross-sectional area reduction, it acts as a brittle material, because this force applied to withstand with this much of cross section. Now it reduce very low value. So with that load, it cannot be withstand. Suddenly fail. Are we clear?
Yes, sir. Thank you.
So that is the thing. So you can see in here in this diagram there is a in a row there is a 6 image. So same thing magnify in here. So you can see that the right side three figures belong to low nominal stresses. Okay, and the left side one, high nominal stresses. So that means if you apply low stresses, okay, that means the lower than endurance limit, assume like something like that, lower than endurance limit. So you will see the cross section like this way. So many failures due to ductile failure. You can see the contour area is very high. But in here, if you apply the slightly larger than the endurance limit alternative stress, you can see this kind of nature. Okay, so you can see this nature will happen, this kind of groove. Okay, this is the no stress consideration. If you don't have stress consideration point and stress razor, you can see that it is highly ductile. But if you have this kind of groove, that is mild stress consideration, as you can be sharp. This is not sharp, it will be very smooth, so it is not it doesn't have high KT value, it's a low KT value. So this is little bit ductile but mostly brittle. But you can see this is there is no this is very sharp, severe stress consideration. Then you can see the failure. Okay, so you can see the failure cross-sectional variation, but this is below the endurance limit. Endurance limit, assume not be too much below, but the very much close to the endurance limit. But if it is slightly higher than the endurance limit, you can see the failure. It is the same conditions in here. Without stress razor, you can see variation. So you can see this without stress razor, always the concave shape, but in here convex side. So you can see. So in here multiple type of crack propagation you can see. In here one single thing, but there is a three and combined later, something like that. So you can predict like that manner just watching the cross section after failure. Okay, so I hope understand about that. Yeah, so I already explained now these things. Multiple crack propagations are there. So yeah, so you can see the contour lines direct to the around this crack initiation point. So this thing I already explained now. Yeah, there is two crack initiations. Okay. Yeah, so I already explained these things. Yeah, so I need to explain this one actually. So this is the actual thing. So you need to know this kind of lesson. So let's see how we can deal with this kind of questions. You can see there is a shaft, it's connected to the wheel. So when it starts to the ground, so what are the load apply on this shaft, and how we can deal this kind of questions, let's see. So I will read the question first, and when I read the question, if you have some doubt or something didn't get clearly, just ask. Okay, the following drawing shows the rear axle of a hypothetical automotive racer with loads applied to the outside rear tire. So you can see as the car traverses a circular test track, force W. W is that weight apply around somewhere here. So the reaction will be applied on the tire. Okay, the force on the vehicle, it is not a W, it will be different, but force apply on the wheel due to that weight is W. It is as a reaction, you can see. It's the weight carried by the outside rear wheels. preview. So assume this is 1/3 of the total vehicle weight. Yeah, that means the total vehicle weight is 3 times, then 3W. The two loads of 0.6 W represent assumed side and tangential loads. You can see here that if you consider this tire, you can see there is a side force, side load like this, and there is a tangential load like this. Okay, so it is inside to this slide in here. If you consider this image, it is inside to the slide. This load and this load, two different things. If you consider this is y-axis, this is s-axis, this load apply on the z-axis. Okay, and this is x-axis. This is side load. So if you consider in here that this load apply inside to the slide. Okay, so there is a 3 load. So as I said, the two loads of 0.6 W represent assumed side and tangential load, which are limited by assumed coefficient of friction of 0.85. Okay. The axle is made of steel having ultimate tensile and yield strength given. All critical surfaces are ground. Estimate the maximum vehicle weight 3W. They already mentioned it. That would permit infinite life under continuous operation at the given condition. What simple design change would substantially increase the shaft fatigue strength? So there are 2 questions. So estimate the estimate the maximum vehicle weight 3W first one. Then you need to give the design simple design change to substantially increase the shaft fatigue strength. So you can see here the shaft connect to the wheel, but the tire somewhere here there is a they mentioned the second moment of inertia and the dimension. You can see the shaft cross-sectional area will be reduced in here. So there is a fillet. Okay, so then this is stress race area. So you need to focus on here, and you need to think about the load type apply on in here. So due to this W around this point, bending will be applied. It will push to the upper. Then due to this 0.6 W, you can see here, it will compress this inside to this axis. If you apply 0.6 W somewhere here, it will like an axial load. So you can, due to this 0.6 W, there is axial load, and same time, due to this distance, it will bend to downward. It will bend 0.6 W downward due to this 0.6 W times this distance. So there is a bending and axial both due to this 0.6 W force. And then due to this load, tangential load, it is inside to this slide. That means z-axis. This if you shift this load to here, it is kind of bending load. It will bend into the slide. Okay, that means it will bend in z-axis. Due to this W and 0.6 W, it will bend in XY plane. But due to this 0.6 W, it will bend on XZ plane. Okay. So just imagine 3D view. Otherwise, you can't understand this. Then due to this 0.6 W, there is a torsion, because if I draw here, so this cross section I will draw like this. Due to this load if you apply load like this, it will try to rotate. So due to this tangential load, there is a torsional load. And same time due to the 0.6, there is an axial load and bending downward. Due to this W value is upward, and due to 0.6 W, this 0.6 W, it will bend to this side. So these are the loading conditions. So we'll apply on that. So there is a 5 type of load: axial load, 2 bendings, and there is a 3 bending types, and torsional, 1 axial load. So you can see we can discuss separately all the loading type we are going to apply on the specimen. Before that, so do you understand what are the load apply on? I mean, what are the load type apply on in here? Any questions? This is due to W. This is not actually W. W due to W bending load, bending stress. This is due to 0.6 W. The side one, I put in S here, and this is tangential 0.6 W, and there is axial load due to this 0.6 side one in here, and this is also happened due to this torsion. So are we have any questions? Anyone? So do you understand the loading types? Even though there is a 3 loads, 2 0.6 W and 1 W load, there is a 5 type of load. Are we clear? So if we have lecture note as well, you can refer that one also. Anyone? Can't you hear me? I don't know.
Yeah, we can hear you, sir.
Okay, did you understand that loading types?
Yes, sir.
Okay. And then separately we will calculate the things. So nominal stresses, vertical W. Okay, so that means this one, the vertical W. I told you it is bending type. So in here you can see the equation. You should multiply that stress by KFB. Okay. So the first example, we know how to calculate the KF for the bending and torsion. So if you find out the KFB, you can substitute here. So I will put remaining KFB here. Later on we can apply here. So bending moment due to this W, this distance. So that is a bending moment. W times 76, but it is in a millimeter. You need to convert to meter. 76.2. So sorry, 76.2 here. So 76.2 times 10 to the power 3 and multiply by W. This is second moment of inertia. Okay. So I hope understand that. So in here we will calculate the this distance d upon 2, the surface stress value. Okay. So normally we get the value for the stresses axially. So if you are going to find out the surface stress, you need to multiply d upon 2. Then there is a 5 d to the power 4, 64. So this is the second moment of inertia, IO. You can put, they put as a Z in here. So then the y value d upon 2, then according to that you can, so you can see there's a d cube only remain. So 32 will be here. So like this. So you can simplify this equation. I mean this term like this. So just W is unknown thing. K we will substitute later. So vertical, due to vertical W, there is a bending. Okay. And the shaft will be rotating. So that's why it's called rotating bending. Then tangential 0.6 W. That means this one. So due to that, there is a torsion. I told you there is a torsion. So you can find out the shear you can find out the torque. You can multiply multiply by 0.6 W by this distance. So you will get the torque T value. You can see torque value in here. And then this is the D upon 2, I told you, surface, at the surface shear stress, and this is the second moment of shear. So then you need to multiply by KFT. It is the fatigue stress consideration factor due to torsion. So W and KFT we will substitute later, but W is unknown thing still. So you have torsion shear stress due to 0.6 W tangential load. Then tangential 0.6 W apply the bending as well on this. It will bend on XZ plane, I told you, inside to the slide. So then that value you can find out. This is the load, so it will bend inside. So then that means that bending moment due to this distance. So it is this load apply on here inside to the plane. So the bending load, bending moment due to this distance. So that's why in here 76.2 times 10⁻3, and this is the load value, and this is second moment of inertia at the surface. So then you can find out the then you need to find out the this KFB and this KFB is the same value. Okay, if you find out the KFB, it's not changed for the this KFB. And then this is lateral load side 0.6 W. Due to that, there's a, I told you it's a compression, axial load compression. For that, you don't want to worry about too much about the equation. It is like a load divided by area. So you know load value 0.6 W and divide by area. So area you should know this is cross-sectional area. So just substitute the cross-sectional area. It is 5R square. So in here 0.5 due to half part because there is a D substitute, D divided by 2. So that is R. So that is why 0.5. So this is the cross-sectional area. You need to when I explained, I told you, even though it's the alternative stress or mean stress, you need to substitute, you need to multiply that stress by K. So in here, K due to axial. So axial load, it's a theta, axial load, fatigue stress consideration factor. So this is the simplification. And due to this lateral force, 0.6 W, there is a bending XY plane to this direction. So it is governed by this distance. So that distance is 254. So multiply by load and second moment of inertia, and multiply by KFB, that is bending one. So the bending fatigue consideration factor. So you will get all the stresses with the W term and KF. So now you can find out the KF. So these are the loads applied. So this is, if you label these stresses as 1, 2, 3, 4, 5. So 1, it is a bending. 2 is a torsion. 3 is again bending. And this is compression. This is bending. So you can see this is 1, this is 4, the axial load, the compression, torsion 2, 3 bending. So if you consider here, it is inside to this plane, and the 5. So these are the load apply on the load type apply on this shaft. Yes, then we can, as I told you, we need to identify what are the mean load, what are the alternative loads in here. So in here, mean load normally you can easily understand. It should be around the axis or apply on the axis. Those are the mean loads. In here, you can see this load type 4, that is in axial compression, it is apply on the axis, that is mean load. And this one, the same center, it is apply around the axis, so that is also mean load. It will not change anytime. So those forces will change. Okay. So this is not change. So, that will change. I mean, if you consider on the shaft one particular point, so when it's rotate, these 1, 5, 3 loads are vary according to the point. Okay, I will draw here, then you can easily understand. So assume this is the cross section. So if that shaft will rotate to this direction, if you label point A and B, so when you rotate this one, A and B somewhere here, okay, 90-degree rotation. So then point A and B, the axial load and the torsional load will not change due to this rotation. But this bending load, due to this bending, stress value will be changed. If the point A, if it is here, that stress value due to bending, that 1, 5, and 3 will change rather than here. But the load value of that stress due to that axial load and torsional load is the same value here and here. So that's how we can identify what are the mean load, what are the alternative loads. So in here, 1 and 5 and 3 are the alternative loads, and 2 and 4 are the mean loads. Then we have 2 loads for the mean load, 3 loads for the alternative load. We need to get the one single mean load and one single alternative load for the Goodman line. Otherwise, we can't find out the multiple type of load in alternative loads and multiple types of mean load Goodman line. We only draw the one particular equations. We should have draw the one single Goodman line. So then what we need to do, we need to get the one equivalent stress for those stresses. So 2 and 4 in here, this is axial load, this is like a sigma x, this is like a tau xy. In here, tau y, sigma y equals 0. Then you can use the Morse circle theory or that equation to find out the equivalent stress, one single stress. It will be the principal stress. So the bending moment, that alternative stress, all the bendings are alternative stress. So 1 and 3 and 5. So in here, 1 and 5 you can easily simplify because the opposite directions, you can 1 subtract by the 5 or 5 subtract by 1, and this is perpendicular to these two. Then you can use the normal you know, if you have the two perpendicular forces, you can get the equivalent forces, resultant force by r squared equal s squared plus y squared, like a Pythagoras law. So this is the equation. Or if you want, you can use the Morse circle theory also. In there, tau xy equals 0. Then sigma x and sigma y only. Then you can easily find out the value. So in here, stress 1 and 2 act opposite to each other, and they hence produce a net bending from 1 and 5. And stress 3 is right angle to 1 and 5. Hence, the resulting bending stress like this. So as I told you, the resulting stress equal that you can say, get the one single stress for these two net stress. So there is a value, and x, that is x square. This is like a y square, and get the square root value. So you can end up somewhere here after simplification. This is the one single alternative stress, sigma A. Okay, this is sigma A. So then you need to find out the mean stress, that means sigma m, one single sigma m. So for that you need to find out the principal stress. I don't know. Otherwise, you need to find the sigma 1 from the Moser. So in here they use equation. So just substitute sigma x and sigma y equals 0. So xy, it is the value in here. In here, this value. So just substitute. Then you will end up the sigma 1 like this. Okay, because you can't simplify this one. Furthermore, this kf, this kf and this kf, these two, even though these two equal, this one is different, so you can't simplify this one. So then what you can do, you can substitute the k values. So in here, even though this is as a table, you in the question at the exam, you don't have this kind of table. Okay? You need to find out all the ratios, and using that ratios, select the proper graphs for the loading type, and find out the ratios, the diameter ratios, and radius divided by the diameter radius. Then you can find out the KT value from the relevant graph, and surface factor from the another graph, notch sensitivity from the another graph. And using that three values, you have the equation for the KF. You can find out this value. So you can find out the each and every KF value for the bending and torsion and axial. So then you can substitute to that KF value the alternative stress, which you derive the equations for the from the early equation. So then KFB, it is for the bending 1.69. So you substitute here, so you will get the alternative stress value. And then mean stress, it is sigma y equals sigma 1. So you can find out the sigma 1 after substituting KFA here, KFA here, KFT here. That means due to torsion and axial. After substituting, you can easily simplify because W is same, then you will end up somewhere here. So you have one single sigma n and one single sigma A. So now you can use that one, but in here you can see we are not going to why isn't KF included in this calculation, because we already used that KF in the stresses. That's why. So you can find out the infinite fatigue strength using this equation. We already find out these things, so just find out the SN value, because we need to know this value for the Goodman line. Then draw the Goodman line. So this is the strength, okay, when KF equal 1, and this is the endurance limit. So sorry, ultimate tensile strength. This is endurance limit. So now we can derive the equation for the line like this. We know the equation, y equals mx plus t type equation. So we already know sigma a and sigma m for this case. In this case, we already find out sigma a and sigma m. We substitute here. So only unknown is w. You can find out w, but this is not the answer. They ask the vehicle weight. It is 3 times from this, so you can multiply by this one 3, and if you want to convert to the kilogram, you need to divide by 9.81. Then you will end up the weight, vehicle weight in kilogram. So that's how we can deal with this kind of questions. Any questions until this point? Do you have any questions? Anything to ask? Anyone? So this type of questions you can see at the exam sometime. So this is the very clearly I can say this is the final stage of your theory what we build up until today. So last question, it was what is simple design changes would substantially
So
increase the shaft fatigue strength.
quick
Yeah.
question, sir.
Yeah.
For the exam, so that does that mean that the previous topics, they won't break down the topics as such? As in, like, it won't be just stress raisers, or it won't just, it'll be a combination like this.
Yeah, it can be. You can't
Okay.
questioning that. You can't raise your hand and you can't tell. So you should be stepwise. You need to do the question. You can't combine those theories. You can't say like that. Maybe they can
Yeah.
be like this thing. Sometimes they can divide it as well. So
They can do both. Okay.
This is the worst case. So this is the maximum level it can reach.
Okay, sir.
So this is the real type questions, no? The real scenario. So until today we discuss some like imaginary situations. So we just get the shaft and apply the load. So we don't know where we can apply this one. But in here you can see what is the shaft, what is the application, isn't it? So on the road vehicle when it's drive, so those are the force apply on the tire. So the shaft will, there's another vibration also there, but vibration you will learn from the another lessons, no? So we assume there is no vibration or something like that. Are we clear?
Yes, sir. Thank you.
Okay. Also, the last question they asked, what simple design change or changes would substantially increase the shaft fatigue strength? I want that from you, your side. So what we can do change the fatigue strength. What we can do? It should be simple design change. Okay. Don't tell we need to change the tire or something like that. So same thing. What is the simple thing you can do? So if you learn this lesson, you can easily answer this one.
Sorry, sir. What was the question?
So you can see here, red color one. What is simple design changes would substantially increase the shaft fatigue strength? So you are the only one represent here. No, there is a 5 students.
No, sir. The other.
So I want your answer. So this kind of questions can be asked in the final exam as well. So this will be the last questions, the part D. Okay, A, B, C, D is there. D will be this kind of. So you should have idea about the idea of the theory. Without not only apply the theory, you should have the idea. So with this question, they will judge your knowledge. So how extent you gather that knowledge, how extent you can use that knowledge. So are there anyone I need to name them? Okay, the Shanal. Okay, do you have any idea?
So the shaft size can be increased.
I couldn't hear.
The shaft size can be increased.
Shaft size? You mean diameter?
Yeah.
Okay. So others? Akhil, Pramit.
So a small tire.
Small tire.
Yeah.
Oh my god. Okay. Viranta?
Well,
So
how
if you put
to the tire length? It's
I
been
could, I
76.2
could.
millimeter.
Hello.
Changing the axle housing to the tire. It's mean the 76.2 millimeter.
This one.
Yeah.
Okay. And there is another one. Fermi.
Still thinking, sir.
Akhil.
so what happens if you put notches along the shaft? So you have stress traces on the shaft.
Which kind of notches?
Not notches, but like for the cross-sectional area where you showed us as in the cross-sectional, where the ductile and the brittle and the crack propagation. So you showed us those circles, and you showed us certain different design mechanisms.
Okay. You mean
if you put those in the shaft?
Okay. You mean that poor design and improved design something? That one?
Yeah. Yeah.
Okay. Yeah. So I'm not. Unfortunately, I should tell. So all the answers are wrong. So that's why I'm telling you. Okay. So this is the last question. This will be the last question in your paper in your that session. That particular question, last part. So they are simple design change. So at that time you can't change the tire diameter or shaft diameter or shaft that the length. You can't change. What you can do that in here. So we always calculate all the things we calculate around here, no, isn't it? We calculate the stresses and K values belongs to here, in here, isn't it? So this shaft cross-sectional suddenly change here. So what you can do, you can put the smooth fillet here. You can machine it. Okay, that KT value you can change according to that. Are we clear? So
Yes.
that one not too difficult, because if you going to change the length of this shaft or diameter of this shaft, it will very high cost thing. Okay, and if you change the tire or that hub or something, it will highly cost. But what you can do is small changes in here of the stress race area. You can fit the fillet, the large size of fillet radius you can change, isn't it, with a small machining thing. Are we clear?
Yes.
Yes, sir.
So that is so if there are simple design changes, okay, in here they significantly mention simple design changes. And the last one, Akhil, no, Akhil, as you told, your answer is a little bit closer, so you can improve the strength using some kind of that technique. That is the part. Yeah, we can use that part also, if you. But
okay.
It is not good for the putting the holes inside the shaft sometime. But you can use another technique to improve the stress distribution. So with that technique,
Yeah,
we
so,
will normally do what we are going to do, change the stress profile
and put the fillets.
Yeah.
So what I meant was, you know how in those little those pieces, the diameter changed because there was a difference in the. I think the design was a fillet, but it changed from one diameter to another.
You want to tell that, but you okay? I understand.
I didn't know. Yeah.
Okay. So anyway, if you have that kind of idea, you need to answer according to that. Okay, because if you put change the diameter or something, it will feel like you are going to change the diameter of the whole section, something like that. So significantly, you mentioned the stress razor areas. So all the calculations we did around this area, because we are not going to calculate the stress this area or somewhere here, because that doesn't want, because normally stress razor area is the higher stress area. So we need to consider the higher stress area, then other area will not significant thing. Okay, is it clear?
Yes, sir. Thank you.
Okay, so I think in the lecture note there is so many questions. I mean, so not so many. There is 3 questions. Okay, belong to water motor, and there is another shaft rotating. So this is the motor projections. So questions and answers available. You can refer that questions, and if you have any questions on it, you can ask next time. So that's all about this lecture. So I can continue the tutorial. So if you're not tired. Tutorials. This one. Yeah, in this tutorial, it's not the actual case, but this is the extent from the tutorial form. So same kind of questions, only difference in here they apply the rotating RPM with the bending point load. You can see then power transmit P equals 40 kilowatts. You can see. Okay, so you need to find the factor of safety with respect to fatigue failure. Can you hear me?
Yes, sir.
Okay. So dimensions, another thing I'm not going to read. So you need to find the factor of safety of this component. So if F equal 5 kilonewton, so they provide the power transmit through the shaft. So what you need to do, you need to find out these ratios. I'm not going to explain that things now. You know everything. So each fillet KT value due to bending and torsion, because there is a torsion, because this is a transmit power and there is a rotating. Okay, so this is torsion. So you need to calculate the KTB and KTT, that means torsion and bending, both values like this. So using this kind of diagram, and torsion you can use this kind of diagram, I mean graph. Okay, so those value you know how to find out now. And Q value for the bending and torsion both. There is a 2 type of load, no axial load, only bending and torsion. So you can find out the torsion and bending notch sensitivity for the shear and bending, and CL and CD. So you know that things, surface factor, and then you need to find out the fatigue consideration KF value for the bending and torsion. You know CSQ and KT, so you can find out the each fillet, and there is a one groove as well. So the groove you need to calculate the same thing, KTB and KTT. So the relevant graphs you need to select, but that you can find out the Q as well using the notch sensitivity graph. Then surface factor you already find out. Then you can find out the KF value for the groove. At the loading point, KFB and KTT, it is equal 1. It is not changed. Then you need to find out the reactions, because we need to know the reactions to find out the bending moments. That's why normally we need to find out the reactions at the support ends. So those reactions you can use force equilibrium and bending moment equilibrium. So according to that, you can find out the F1 and F2. You know how to find out that thing. So F is, yeah.
Sir, if F is unknown, how can we find the?
F is given. They provide us. F is unknown. What you need to do, you need to find out the you need to find out the reaction with the F like this.
Okay.
So if you know, you can substitute here. So you can see 0.4 F. So that when it is 5, it is 2 kilonewton, like that. Okay. Then that this is nominal stress, the local area, any point you can find out using this equation. Now it's very familiar. So if you know torque, so if you know the power transmit through the shaft, you can find out torque using this equation. If you don't remember, now you know that, because P equals T times omega. That means the power transmit through the shaft. They provide the power transmit through the shaft, so you can find out the torque. Okay. So when you use that one, in here you can see the omega, they provide as the RPM. Okay, you need to substitute here, not as a RPM, radians per second, you need to substitute. So if you know the number of cycle, it is N, you can find out the, so because omega equals, you know how to find out the RPM. RPM means round per minutes. Okay, so round per minutes, when you convert to the radians per second, just unit conversion. The one round means 2.5. Okay, so there is a n number of cycles within minute. So when you convert to the second, you need to divide by 60. So omega equals 2.5 n divided by 60. So when you substitute omega here, is 60p divided by 2n5. Okay, so this is the using this equation you can find out the T, because we need to know the torque to find out the shear stress. So this is the shear stress equation. So you just substitute here torque with this equation. So normally you need to derive this kind of equation for the particular equations. Don't substitute every time in here. Use derive this kind of general equation for the particular equations, and you can use everywhere. You can see in here they use that equation. So these are the two equation we need to use for the nominal stresses and shear nominal stresses and shear stress. Sorry, nominal stress and nominal shear stress. And then what you need to do, the stress raised area, you need to find out the alternative stress and shear stress. So alternative stress due to bending, you need to multiply this value by KFB. And shear stress, it is act as a mean stress. I told you, if it is a shaft, if it is a rotating power transmitter as a rotating, so it is symmetric around this axis. It is act as a mean stress. The bending load act as a alternative stress. So it will not change. This will not change. This shear stress not change point to point. That's why. So it is get as a mean stress. So that's why they mention here tau m. Okay, tau m means the mean stress, mean shear stress. So mean stress act as a shear stress. So the fillet 2, that means 0.5 millimeter fillet, you can find out the bending load. That is alternative load actually. So you need to multiply that KB. But when you substitute the bending moment each fillet, it will be different. Okay, so this fillet you will use this reaction value and this distance. If you use this fillet, you need to find out the bending moment with this load value, this reactions times this distance. Okay, you can see here bending load value will be different. Same equation, bending load value will be different, and the fillet KF value also will be different according to fillet. You can see other values are same, and tau m, same equation in here, but KFT in here you can see KFT only changing, other things same. Due to fillet only that KF value will be changed, and that the groove same equation, the bending moment only change. You can see If you want to find out the bending moment from this direction, you can find. If you want this direction, you can find. So the loading, sorry, groove, at the groove, you can find out the alternative stress due to bending, and shear stress, it is a mean stress, shear stress due to torsion, like this. And the loading point, Kf, Kb is equal 1. Don't worry, they just say Kb, Kat, Kft, because it is equal 1. So you can just substitute here. At the loading point, bending moment, you need to substitute here. In here, you don't want to substitute anything because P is in here, there is Kf equals 1. So same answer without this one in here, same thing. So now you have all the stresses and shear stresses, and so you need to consider check which stress is higher. So you can see when you consider the loading point and groove until this point, this is the higher one, 146, and this is, yeah, 146 is the highest one. Okay, for the alternative stress is higher at the groove, but when you consider the shear stress, this is 24, 51, 64, 65, this is 58. That means the 0.5 pillar shear stress is higher, you can see. So that's why we only need to consider 0.5 pillar and groove, because shear stress is higher for the pillar, and the groove, the norm stress will be high, alternative stress will be high. So then you need to find out the strength without substituting Kf here. So we know the CLCT value, so you can CS, you can find out the endurance limit. Then you can draw the Goodman line like this, and if you want, you can find the equation, because we already know ultimate resistance and endurance limit values. Substitute here, so they simplify here after substitution. So this is the equation. Now what we can do, so these equations belong to this one, but you can get the equation for this one as well, because this is parallel to this one, same gradient, then only intersection will be changed. Okay. So this is shifted downward due to stress raises. So you can find out new actual line. This is not a Goodman line, but you can find out the actual line using this same gradient. So you can see same gradient, and sigma A1, this is the intersection, and you can find out at any point of this line using this equation, same gradient and intersection. If you know, this is sigma A1, this is the new alternative stress. So you just substitute sigma alternative stress in here, then what you can do, you can find out the max. So each pillar and groove you don't want to consider, because we already know the 0.5 pillar is the maximum shear stress. It is shear stress is a mean stress, so sigma m is the mean stress. So you can substitute here and find out the sigma a and sigma m we know. So you can find out this maximum stress. So you can see this equation, they rearrange subject to this one. So then sigma a is, if you find out 0.5 pillar, this is sigma a, this is sigma m. So just substitute here, you can see substitution, then you can get the alternative maximum stress. At the groove also you can substitute in here. So from these two you can get the maximum one. So this is the maximum one at the groove. So factor of safety, you need to consider the maximum one. Then you need to divide the maximum stress it can apply on that one, that is yield stress. They provide us that value. What is the value? The 300 the value, I didn't remember the value. Here, that is the maximum value, this value. So you need to divide this value from this one. So that is a factor of safety. So this is the operating line, this is the Goodman line. Okay, because of K, that stress razor, this will be shifted to downward. Okay, so this is the factor of safety. So you can find out the factor of safety. It is equal to 2.09. So any questions?
No, sir.
No, everything is clear. Wow. So in these questions, you can deal with, I think we already discussed tutorial number 4, this question. In here, they apply the axial load. You can see this is the constant load. Okay. And they, same time, they will apply the strength and axial load. Yeah, you can see estimate the compressor lifetime cycle when mean load is 18 kilonewton and the alternative load 10 kilonewton. So alternative and mean load, earlier there wasn't a alternative load, sorry, mean load. Now there is a mean load as well, so you can calculate it. So you have the answers with you. Just go through your tutorial. So if you have any question, you can ask next time, or if you have any questions until this point, you can ask now. There is 5 students, so I don't want to name everyone. Just if you have, raise your hand and ask question.
Excuse me, sir.
Sorry.
Sir, in the first question,
yeah,
why we consider the 0.5 millimeter radius in the to construct the Goodman line?
0.5 millimeter fillet.
Yeah, fillet.
Yeah, because when we consider the, I told you, if you consider the stresses, so if you draw the SN curve in here, we can't draw the SN curve for the each run, but you can draw this. You can find out the strength for this fillet if you want. Okay, so if you find out the strength for this fillet, so SN curve will be the cross each other. So it will be something like this and this. So did you attend to the previous lecture? So I told you if it is cross, the minimum point and maximum point, if it is a different two line, 10 to the power 3 cycle, minimum value will be provided for the SN curve. You need to consider that curve, and if different curve will be provided the 10 to the power 6 cycle strength, minimum value provide. If it is provide different curve, you need to consider both curve and find out the values for the both curve and just check with which one has a minimum value. Last time when we discussed the tutorial, I told you. So in here also, you can see the mean stress will be higher. When you consider the stresses, we normally consider the highest stresses. So higher stresses for the mean stresses. That means the shear stress is the mean stress. So mean stress will be higher at the 0.5 millimeter fillet. Okay, but alternative stress, it will be higher at the groove. So we need to consider both. And out of these two, we need to get the maximum one, like this. So you can see. So you need to do the calculation. No, okay. If you want, you can do the each fillet and each groove and loading point alternative maximum value, you can find out like this. But in here, what we are going to do, we are going to know, minimize, narrow down the point we are going to calculate. If you can easily see somewhere here at the groove, maximum alternative stress and maximum mean stress at the groove, you don't want to do the calculation for the point, just do the calculation for the groove. But in here, the one pillar and one groove has a separately reach to the maximum stresses for the mean stress and alternative stress. So you need to do the calculation for the groove and pillar separately. So when you're going to apply the pillar, this equation, you need to substitute sigma A and sigma M. Sigma M is at OMX. Sigma A means you are not going to apply in here groove value. Okay, the maximum alternative stress 146.0.9 megapascal at the groove, but you are not substitute that value in here. You need to substitute at the pillar sigma A value, alternative stress, and at the pillar maximum shear stress value.
Sigma.
So then you will get the maximum alternative stress. Okay, you are not going to combine those two, separately calculate the both fillet and groove and check whether alternative maximum value for the each point and which one is higher. So the at the groove it is high, so you need to consider at the groove only then. So you need to calculate the factor of safety at the groove. Are we clear?
Okay. Okay. Thank you, sir.
Any other questions? Okay, then I will finish here. If you don't have any questions, okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.